Kinetic molecular theory is the simplest model for the behavior of gases. Here we're modeling the gas as a collection of particles. Those could be molecules or atoms, depending on the gas. And these particles are in constant motion. So the idea here is we look at these particles, and they're like trailing lines to indicate movement, right? So this particle, the particles are going to move in a straight line because they're not moving through air. They are the air. They're moving through nothing. So this particle has nothing to run into until it hits the wall of the container. It's going to hit the wall and it's going to bounce off. Now, occasionally, two particles will collide and they will bounce off of each other. So when they collide, the collisions are elastic, no energy is lost, and so they just bounce off and keep going. There are some assumptions. So the size of the particle is negligibly small. So gases are like Wyoming. The size of the people is negligibly small compared to the size of the whole state, right? So this is assuming that the gas particles occupy no volume even though they have mass. Do they occupy volume? Yes, they do. But it's so small that it doesn't matter. There's so much empty space. To give you an idea of the empty space at standard temperature and pressure, argon atoms, which are relatively large atoms for gases, occupy only 0.01% of the volume of the gas. 99.99% of it is empty space. If the argon atom was the size of a golf ball, its nearest neighbor would be 4 feet away, and in between would be absolutely nothing. Lots and lots of empty space. So would it matter at that point if the golf ball was like a baseball? Not really, right? The size of the particle just doesn't matter. Average kinetic energy is directly proportional to the temperature in kelvins. So you raise the temperature, the average speed of the particles increases. What's important here is that this is the average speed. They're not all moving at the same speed. It would be convenient to think of it that way, but it's not true. So there's an average speed. You increase the temperature, you heat up the gas. On average, the particles are moving faster. The average speed goes up. When particles collide with each other, the collisions are elastic. So this is like two billiard balls running into each other rather than two like round balls of clay, right? Two round balls of clay bump into each other and they're just going to kind of go funk and they're going to stop moving, right? But you roll billiard balls at each other and they're going to bounce off, right? And they're mostly elastic. In gases, it's completely elastic. The particles can exchange energy, but there's no loss of energy. So the gas particles are kind of like the little blip on the Pong game. Do you guys still know what Pong is? One of the very, very first games, video games. And you had this little bar at the bottom and this little blip, and you're trying to keep the blip going, right? And sometimes you could get it just right, so it would just sit there and go forever, right? It never slowed down because there's no friction, there's no wind resistance, there's no loss of energy in collisions, and gas particles are just like that. So here we have elastic collision versus inelastic collision. The total kinetic energy here is conserved. So you can have a situation where the balls are coming in at equal speeds, they bounce off of each other, and they leave at equal speeds. You could have the ball coming in and the other one was only moving a little bit. Now this one's going faster and that one's going slower, but the total amount of energy is the same. Here we have two lumps of clay, and when they bump into each other, all their kinetic energy is gone. It's dissipated as heat. There's no movement anymore. So gas particles are like billiard balls. So kinetic molecular theory explains a lot of the things we've been talking about. So gas particles are constantly moving, and so they're continually striking the sides of the container, and they have a force when they do that. They hit with a force. It's very tiny, but they do it a lot. So the result of the many particles in the gas sample hitting the sides is we get this constant pressure. So we talked about this earlier. The pressure is equal to the force divided by the area. So the force comes about from the particles hitting the walls of the container, and this would correspond to the area of the container surface. The theory explains Boyles Law. Boyles Law says the volume of a gas is inversely proportional to the pressure. Well, if you decrease the volume, you force the molecules into a smaller space. And in that smaller space, they're going to collide with the container more frequently, which is going to increase the pressure. Yeah? Pardon me?
F and A?
Force and area. The units could be lots of different things. So pressure is force divided by area. The one that probably makes the most sense to us is PSI, pounds per square inch. That's the pounds per square inch. And so I'm not sure if you're aware of this, but on a linoleum floor, a moderately sized woman wearing spike heels can actually puncture linoleum with their heels. Right? Because if you've got, say, 100 pounds, the woman only weighs 100 pounds, but her heel is only a quarter square inch. That's 400 pounds per square inch of pressure. That's a lot. Whereas if you have a regular shoe with a larger heel, when your foot hits, the pressure on the linoleum is spread out. The force is spread out, and so the pressure is less. Right? So this is why, say, if your significant other were to lay down on top of you, right? So there's pressure, right? You're like, ugh. But it doesn't like hurt or anything, right? There's just pressure kind of all over. But what if they stand on your stomach with one foot? You can imagine that would not be good, right? Way too much pressure. This is what made me think of this is my dog. She's about 42 pounds, and sometimes she'll just like take off. And, you know, there's like one or two little feet on your stomach as she jumps off of you on the bed. Ugh! Lots of pressure. Sorry, went off on a tangent. Charles' Law. Volume of a gas is directly proportional to the absolute temperature. So the theory says that if we increase the temperature, the average speed, the average kinetic energy of the particles increases. If we're going to keep the pressure the same, which is what we're doing with Charles' Law, then we have to increase the volume because those particles are moving faster. They're hitting more frequently and they're hitting harder. And so the force is greater, we have to expand the area. So the gas has to occupy a greater volume at higher temperature. Avogadro's Law, gas volume is directly proportional to the number of gas molecules. So if we have a container and we keep the pressure constant and we add more gas, in order to keep the pressure constant, we have to increase the volume of the container. Daltons Law. The partial pressure, the sum of the partial pressures is equal to the total pressure. So kinetic molecular theory says the particles have negligible size and they don't interact with each other when they bounce off. It's completely elastic. So particles of different masses are going to have different kinetic energies particles of different masses have different velocities, but they will have the same kinetic energy. Kinetic energy is 1/2 the mass times the velocity squared. So the kinetic energy of a gas is directly proportional to its temperature. So because the total, my brain, where was I going with this? Dalton's Law. So we can have particles that have different masses, but they have the same amount of kinetic energy. And so they're going to exert the same amount of pressure. It doesn't matter how big the particles are. The average kinetic energy is the same, so the total pressure of the collisions is the same. If you have big particles, they're going to be moving slower, but they're going to have the same kinetic energy as a smaller particle. Less mass will be moving faster. And they'll hit more frequently, although not as hard, and the pressure ends up being exactly the same, regardless of what particle it is. The ideal gas law. There's a derivation of this in the textbook, which is really cool, but I'm not going to go over it in class. But the theory predicts behavior that's consistent with observations and measurements of gases. Scientific theory is the most powerful kind of scientific knowledge. Now, the model does break down under some conditions, but when we look at those breakdowns, we actually learn even more about gases. So the average kinetic energy of gas molecules depends on their mass and their volume, and so we have this general equation. Kinetic energy is 1/2 the mass times the velocity squared. If gas particles have different masses, the only way they can have the same kinetic energy is if they have different average velocities. And the average we use here is kind of a weird one. It's a root mean square, and it's very similar to the average, but it's kind of different. So in a gas mixture at a given temperature, the lighter particles travel faster than the heavier ones, but they have the same energy. So you can have the same energy and different masses and velocities, but the combination of them gives the same energy. So URMS is the root mean square velocity. It's a special kind of average, which we're not going to go into. But here's a useful equation. The root mean square velocity is proportional to the square root of 3 times RT divided by the molar mass of the particle. Now, what's important here is that the molar mass is in kilograms per mole, and we're using a different value for R with different units. So 8.314 joules per mole Kelvin. Molar mass is in kilograms per mole. We need these units so that it works out and we get a velocity in meters per second instead of some other weird combination of units. I'll give you this equation and I'll give you these values. Well, I'll give you this. I won't necessarily remind you of that. Lighter particles have broader distributions. So here we have the relative number of particles with the indicated velocity versus molecular velocity. And oxygen is heavier than hydrogen. And so we have more of these oxygen molecules going at lower speeds to have the same average kinetic energy. And with the hydrogen, we have more at higher speeds. And that makes sense. What doesn't immediately make sense is, why isn't this hydrogen just a similar shaped bell curve just moved out? But they just broaden out. So as you get smaller and smaller molecules, the range of velocities spreads out. It doesn't just move over. If we increase the temperature of a gas sample, we see a similar effect. So here we're looking at a single gas at 273, 1,000, and 2,000 Kelvin. So as you increase the temperature, the average velocity increases. And we can see that the main part of these peaks moves out to higher and higher velocities. But the peak also broadens out.
So the lower the temperature, the higher?
Yeah. The lower the temperature, the more uniform the velocities are, and so we'll get a more narrow distribution. So this is stuff that, especially if you're majoring in a science field, this might be significant, and it might interest you. For most of you, this is probably useless, honestly. But it's in the class, so I told you about it. Calculate the root mean square velocity of gaseous xenon atoms at 25 degrees Celsius. So we're going to use the equation for root mean square velocity. U RMS is equal to the square root of 3 RT over M. And the R here is 8.314 joules per mole Kelvin. And molar mass is in kilograms per mole. So what's the molar mass of xenon? It's 131.3 grams per mole. I need to convert that to kilograms. I got 8.314 from this slide. Yeah, it's okay. So if I convert this to kilograms, kilograms on top, what it means on the bottom, so 0.1313 kilograms per mole. Temperature needs to be in Kelvin. So I collect all those pieces. And I've got 3 times the ideal gas constant. And it's a different number because it has different units. It's the same quantity. There's R, there's my temperature, and then this is divided by 0.1313 kilograms per mole, and the square root of the whole thing. So if we look at the units here, the moles are going to cancel out, and the kelvins are going to cancel out, but the joules and the kilograms do not cancel out. And so we can do the math here. 3 times 8.314 times 298 divided by 0.1313. Five, 6, 608 joules per kilogram. The square root of that. I don't expect you to be able to simplify those units, but I'm just going to show you that it works out. So you can say, well, it'll be fine. A joule is the same as a kilogram meter squared per second squared. If you've had physics, that might be a little familiar. And so what we've got here with our joules divided by kilograms, that is kilogram meters squared per second squared divided by kilogram. And the kilograms cancel out, and I've got meters squared per second squared. So instead of this, I can write meters squared per second squared. So then when I take the square root of that number, I get 237.92 meters per second. Meters per second, or 238 meters per second. Any questions? Yeah.
So you said you're going to give us that equation, but you said not necessarily the units? Or?
I'll give you the equation, and I'll give you the different value of R.
Yeah.
You need to remember that the molar mass is in kilograms. Yeah. Can I go back 238. Yes, I can. You don't need to worry about this. Yeah. I know that some of you like units, and I just want to show you that I'm not making stuff up. Which sample of an ideal gas has the greatest pressure? Assume that the mass of each particle is proportional to its size and that all the gas samples are at the same temperature. It looks like they all have the containers are all the same volume. So these particles are heavier and these particles are lighter. These look about the same size as those. Which of these is going to have the largest pressure? The biggest pressure. Well, let's not just guess. Does the size of the particle affect the pressure? No, it doesn't. So it doesn't matter what size the particles are. What matters, PV equals nRT. We've got pressure, that's what we're trying to figure out. The volumes are the same, and the temperatures are the same, and the ideal gas constant is the same. What's different? How many particles? More particles, more pressure. So the answer is C, because it's more particles. These two have the same number of particles, and so even though these are big and these are small, those pressures are going to be the same.